Hey, were there any questions? No questions. We're going to do a Le Chatelier's experiment today. Le Chatelier's is a systems at equilibrium. So the system that could be at equilibrium would be like two water wells like this. If we say on one side is the reactant, on the other side is the product, then we're going to have an equilibrium situation where the two wells are filled to the same height. You know, if one side's higher, then it's going to push water in one direction or the other direction. It doesn't always have to be like this, though. This is a case where the reactants and products are kind of 50-50. You know, we could have equilibria that favor the products. If it heavily favors the products, it might look something like this, you know, where we don't have much reactant, but we have a lot of product. Okay, again, this is going to be an equilibrium as well. So we're going to have water that can go forward, and we can have water that can go backwards. When the two rates are the same, then we've established this equilibrium here. And the same thing here, water can go forward or it can go backwards between the reactants and the products. But in this case, the products are favored. In other equilibria, the reactants will be favored. So it'll look something like this, where it's mostly product, maybe just a little bit of reactant. And once it establishes equilibrium, then we have the forward and the reverse the same in terms of rate. Okay, when we initially start this, we put in reactant, and so there's only water on this side, and the water will flow forward, so we'll have net forward reaction until we reach this balance, and where it can go uphill or downhill either way. And so this is another way of visualizing it. And so in Le Chatelier's principle, what we end up doing is we end up perturbing this equilibrium. So for example, if I dump more water here on the reactant end, then what's going to result is a net shift to the right. That is, water is going to flow to the right in all three scenarios here. So if I add more water here, this level is going to raise up too high, and then we're going to get net forward, and then eventually we're going to strike a new balance. And that new balance will be the new equilibrium. And the new equilibrium, both sides will be a little bit higher here. In that case, the same thing here. Another way I could shift this to the right, that is, get net forward migration of water or product formation, is to remove some of the product here. So if I start removing the water out of here, then this is going to go forward in that sense. So those are the typical techniques we use. Likewise, we can add or remove reactant as well, product, to shift it either way. And so if I add more product, it will shift it to that. If I remove reactant, it will shift it to the left. And so let's take a look at today's experiment. So the first thing we should do is we should take a look at the equipment, medicine droppers. Medicine droppers are okay. What happens is the rubber bulbs on these tend to get brittle, and so they don't work as effectively. If your rubber bulb is cracked like this one, you can get a replacement. Or you could use the plastic pipettes. We have some plastic pipettes like the ones in the beakers on the back there. Those are better. 250 beaker, some beakers, grad cylinder. No, actually, we don't really need a graduated cylinder. This is kind of a qualitative experiment. Measuring volumes using a graduated cylinder takes time. We don't need to take that time. We just need approximate, So for example, with the plastic pipettes in the back, one squeeze of the bulb is about a milliliter. And so if you need about a milliliter, I just do one squirt. Let's see if I have a plastic pipette. I don't. And so that's about a milliliter. One squeeze, suck it in, squirt it out. Or you could do drops. It depends on how much time. To count out 20 drops is a milliliter. And so that takes too much time. I just do a squeeze for a mil, half a squeeze for a half a mil. Something like that. Okay, let's see. Test tubes, Bunsen burner. As far as the chemicals go, we take a look, like copper 2 sulfate, etc. Nickel 2 chloride, cobalt 2 chloride, potassium iodide, sodium carbonate. Sodium carbonate is pretty safe. Potassium iodide is relatively safe. The copper, nickel, cobalt salts, you don't really want to touch those. As far as the anions go, sulfate is not that hazardous. Chloride's no problem. Iodide's not much of a hazard. Carbonate's not much hazard here. Then we get to silver. Silver nitrate is hazardous. Silver is a heavy metal, and it's also an oxidizer. And so if we want more information about silver nitrate, where would we look? And the place that we typically go to is the MSDS. It's now called the SDS. MSDS stands for Material Safety Data Sheet. Whenever you buy a chemical, it's required that you also include the MSDS with the purchase. So we have a bunch of these depending on where we get it. In fact, this one is this one's from this supplier here, Lessick Common Chemie. And initially, they just give you the names, nitric silver salt, nobody calls it that. Lunar caustic, maybe people call it that. I don't know. But we call it silver nitrate. The molar mass, the percent by mass, formula, reportable quantity, this is just the quantities they sell. And the purity, the higher the purity, the higher the grade, the more expensive. The lower the purity, the lower the grade, the cheaper. We use the cheaper stuff. We use the technical grade stuff. Technical grade's like 98% pure. This is pretty good. This is 99.9. If you want the highest grade stuff, it usually has 6 nines, 99.99999% pure. That's high purity. Usually on an attachment to this, we have the analysis. So this is 99.9. What's that 0.1% consist of? And so they analyze it, and normally they report that, what the major impurities in this are, because it's important to know if those will interfere with what you're doing. And then we look at the hazards. The hazards are given by these NFPA values. NFPA is National Fire Protection Association. And they come up with signs like this. This is an NFPA sign here. The blue is the health, the red is the fire, yellow is reactivity here, and this is special hazards. The special hazard in this case is water reactive. Like for example, if there's a fire here and we have water reactives, you don't want to use a fire hose and water to put out the fire. Otherwise, you can have a violent reaction. The NFPA ratings range from 0 to 4. 0 is safe, 4 is hazardous. And so when we look at the health rating of silver nitrate is 3, which is potentially hazardous here. Let's take a look at what they say. Elevated causes eye and skin burns. And so it's an elevated risk here, and it causes eyes and skin burns. Even small amounts will stain skin. This is a common thing. Did I tell you about the student I had in, I think, Chem 4? And the student accidentally spilled some silver nitrate all over their hands. They got black splotches. Did I say that? No. It stains your skin black. Why does it stain your skin black? Because the silver is an oxidizer, your skin is a reducer. You're electron rich, you will burn, in a fire, you'll burn, basically, your fuel. And so you have an oxidizer like silver ions, a reducer like your skin, you're going to get a redox reaction. what's going to happen is the silver ions are going to take electrons from, they're going to take electrons from your skin and precipitate out silver metal. Let me turn this down. Tiny crystals of silver metal look black, and so those get incorporated into your skin, and basically it's very hard to wash off. So this student had an important job interview right after lab, and they told me that they had been washing for 30 to 45 minutes their hands, but the black stains wouldn't come off, and it was because of this silver nitrate. So unfortunately, well, we'll see what happens with the stains here. All right. Even small amounts will stain skin. Inhalation will cause burns to the upper respiratory tract. And so, you're going to get some redox reaction going on. It's going to cause burns. Sure. Flammability rating 0. This is the oxidizer. You know, air, is air flammable? No. Air is the oxidizer. You need the oxidizer and the reducer. So the silver nitrate's the oxidizer part. It can support combustion, you know, because it's an oxidizer, but you can't burn the stuff as a reducer. Reactivity rating 0. Well, it depends on what you're reacting it with. It's normally stable, so it doesn't really decompose, even under fire exposure conditions, because it's an oxidizer. Reactive with water, and so the reactivity can increase. I mean, nitrate is a pretty decent oxidizer, especially if there's acid around, so that could be potentially dangerous. Lab protective equipment, safety goggles and or face shields, latex. I prefer nitrile gloves, they're more chemical resistant, good ventilation. Storage color yellow. You know, yellow, we want to mix the yellow chemicals with yellow chemicals, but not with other. You know, that way we can avoid unintentional reactions. Okay, let's look at the first aid measures. Inhalation, remove the pressure. This is like if we're working with solid silver nitrate. Solid silver nitrate you can buy in a powdered form, and so you might create a dust cloud. If you create a dust cloud, then you want to avoid inhaling that dust. The dust consists of tiny crystals. These crystals will sting the nasal passages. Get medical attention as soon as possible. Ingestion. If swallowed, do not induce vomiting. Give a quantity of milk or water containing table salt water. Get medical attention immediately if the quantity ingested is more than a gram. I think that's what it says there. Skin contact. Wash immediately with soap and water for at least 15 minutes. The stains usually vanish in a week. So, you know, within a week later, you're going to shed the skin, and you know, the black stains will go away. They don't vanish. They just rubbing the skin off. Stains on fingernails can be buffed away. So if you get some on your fingernails, then you can get rid of that quickly. If you get some in your eye, that's more of a problem, because you don't want tiny crystals of silver to precipitate in your eyes. You aren't going to be able to wash that away. So get medical attention immediately. Immediately flush eyes with plenty of distilled water for at least 30 minutes. We don't have distilled. We're just going to use the next best thing, tap water in this case. Tears will cause a film to form on the eye. So I'm not exactly sure what they're talking about there, but 30 minutes. 30 minutes is kind of long. The normal protocol is for 15 minutes of eye wash. To sit under the tap for 30 minutes is going to be uncomfortable. So we have these. We have a 4 outlet eye wash fountain over here you can use, but you might want something sooner than walking over there. And so essentially it's going to cause painful burns to your eyes. And so we have these eye wash fountains here. And this is a flex tube, and then you can just wash your eyes. When I worked in the lab all day, I normally wash my eyes. Maybe at least once or twice a day, depending on how many irritants were in the air, you know, just to wash out. Otherwise, my eyes would start to burn after a while. And so we have eye wash. You'll want to flush those initially because they have caps on them, but sometimes the caps are off there, like this, and stuff can get in there. So flush it initially and then wash your eyes out. But that's 30 minutes. That's a long time. So you want to avoid getting the stuff in your eyes. And so we're going to need safety goggles today. There's a box of safety goggles in the back corner over there. You're welcome to take any of those. But what you're looking for is you're looking for good splash protection. Most of the chemical exposure to eye comes from below here. And so you want a good seal along your cheeks. So if something does splash up, it doesn't get into your eye. It doesn't offer much side protection, but we don't get too many splashes or whatever from the side. We have to watch out because sometimes people are working with test tubes like this, your neighbor, and they have the open end of the test tube pointed towards you, and then it could splash in this way. If something were to, let's say, get too hot in the test tube or splatter out, we want to watch out for that. Okay, firefighting measures. We aren't going to fight a fire here. If there's ever a fire in the lab, we're just going to evacuate. Make sure the doors are shut. There is a fire extinguisher over there. There's a fire blanket. The fire blanket is for putting out fires. If your clothes catch on fire, then you want to go to the shower over here. And so this is the safety shower. Just stand below this and then pull down the handle here. And that'll put out the fire. If your neighbor is on fire or has stuff in their eyes, help them. Help them over there. Eye wash and safety shower. Simultaneously or something. I don't think we'll have to worry too much about it here. Okay, use an extinguishing agent suitable for surrounding fires. Wear SCBA, self-contained breathing apparatus. We don't have any self-contained breathing apparatus in the lab here. Explosion hazard. Reaction with ammonia will form explosive fulminating silver. So watch out. Silver ions, oxidizer, ammonia, reducer. Ammonia is electron rich. So we got to watch out for that. It's the same thing. In the house, you never want to mix bleach with ammonia. If you mix bleach with ammonia, bleach is an oxidizer, ammonia is a reducer, you're going to get potentially violent redox reaction. We have another strong oxidizer here, nitric acid. And so we have two strong oxidizers. The silver nitrate is only 0.01 molar, so it's not very concentrated. The nitric acid is 6 molar, a bit more concentrated. 6 molar is still considered dilute, but nitric acid is a great oxidizer. And so if you spill silver nitrate, you'll get black stains. If you spill nitric acid, do you know what color stains you'll get on your skin? Yellow stains. And so nitric acid, it'll oxidize your skin. Again, the skin's not too hard to oxidize. It'll oxidize your skin and produce oxides of nitrogen, like nitric oxide. And that nitric oxide can complex with chemicals in your skin to produce a yellow color, yellow complex. And so, after a lab like this, people have black spots and yellow spots over their skin due to spilling silver nitrate and nitric acid. Hydrochloric acid. I've spilled lots of hydrochloric acid on my hands. It's not that bad as long as it's dilute being less than 6 molar or 6 molar, even 6 molar. But what you want to do is you want to wash it off. It's the same thing with nitric acid. Wash it off with soap and water. They say to wash off for 15 minutes. which you could do, or what you think is sensible, longer or shorter, depending on the circumstances. But one of the hazards with HCl are the fumes. We're going to be using concentrated HCl. The concentrated HCl is in hood 6. The nitric acid is in hood 5. The ammonia is in hood 7, and the waste jug is in hood 8. Right. But the hydrochloric fumes. So if you have some hydrogen chloride is a gas, and you mix it with water, you make hydrochloric acid. And if you just let the hydrochloric acid sit there without a cap on, the HCl starts to fume off the top, and then you can inhale the vapors. So some people are really sensitive to HCl because it really is very irritating to your mucous membranes and your nose, throat. And so watch out for the fumes from this stuff. We're going to be using some concentrated 12 molar HCl. The 12 molar is fuming a lot. And so the nice thing about doing it in the hood is the fumes will be captured by the hood and then exhausted outside. If you take the 12 molar outside the hood, then you might be breathing in the fumes, which wouldn't be very comfortable. It'd be very uncomfortable. We're also using 15 molar ammonia. HCl is not that powerful of an oxidizer, so I don't expect any redox reaction. If we have HCl and ammonia, we're just going to form ammonium and chloride. That's it. But ammonia is a good reducer. So if we have nitric acid and ammonia, that's a different story, because nitric acid and ammonia can make oxides of nitrogen, like NO, NO2, etc. And those are toxic. And so don't mix nitric acid with ammonia, or if you do mix nitric acid with ammonia, do it inside the hood, because you're going to have two reactions that occur. One is the acid-base reaction. Nitric acid neutralizes the base, ammonia. But two, we could have redox reactions. Nitric acid oxidizes the ammonia to make oxides of nitrogen, which are toxic. And the same thing. Don't mix silver nitrate with, well, actually, we are going to be mixing silver nitrate with ammonia. But under certain conditions, that could create a redox reaction, which could create potentially explosive compounds. But under these conditions, it's not. We're not going to worry about it. All right, so those are the chemicals we're working with. Take a look at the first reaction here. The first reaction is we have this light blue copper tube. Well, how do you name that? Tetra aqua copper 2. Tetra aqua copper 2 ion. It's light blue. We can get that from copper 2 sulfate solution. And then that's going to be in equilibrium. We call this equilibrium. It's going to be in equilibrium with this. What's this called? Tetraamine copper 2. Tetraamine copper 2. Which side do you think is favored? Which side do you think is the downhill side? Well, one way to tell is this. Which one is a better Lewis base? Water or ammonia? Ammonia. Well, ammonia is better at Lewis base. It's because ammonia is what we call a nitrogen donor. Water is what we call a what donor? Halide would be like chloride, bromide. And so water would be, what atom in water is donating a lone pair? Is it the hydrogen or the oxygen has the lone pair? Oxygen. And so this is the oxygen donor, this is the nitrogen. Nitrogen donor is better. And so it should be downhill in the forward direction. So when we add ammonia, we expect it to react and go to the right. Now, that's exactly what's going to happen. You add the ammonia, and eventually you're going to get dark blue solution. This is aqueous, so this should be a dark blue solution. And so you want to keep adding enough ammonia until you see a dark blue, deep blue solution over here. And then we're done. Then what we could do is we could do two things here. We could shift it further to the right. If I want to shift it further to the right, I just keep adding more ammonia. The more ammonia I add, the more it shifts to the right, dark blue. This Le Chatelier's. The other thing we could do is we could shift this back to the left. How could we shift it back to the left? Well, one way we could shift it back to the left is by adding, well, adding water is tricky because what we need to do is we need to change the concentrations. So if we just add water, this doesn't change the concentrations over here, but it doesn't change the concentration of water. Water, do you know what the molarity of pure water is? It's, if I had 1,000 grams of water, it'd weigh 1,000 grams, but it would also be about 55.5 moles, 18 grams per mole. And so 1,000 grams is 1,000 milliliters, which is a liter, so it's about 55.5 molar. So even if I make more pure water or lose pure water, it's not going to really change the concentration. I could add more of this, but I'm not. What I'm going to do is I'm going to change the amount here. If I remove ammonia, and so if I remove the ammonia, how can I remove ammonia? Well, you know, I have to think, what are the chemical properties of ammonia? What does ammonia like to react with? Yeah, it could react with silver. It could react with, well, ammonia, well, let's think about it. Is ammonia an ion, let's say? No, so maybe, probably we won't look at metathesis right now. Is ammonia an acid or a base? Well, it's actually both, but it's much better base than it is an acid. And so one way of removing ammonia is by reacting with an acid. So if I take ammonia and react it with a strong acid, I'll create ammonium. Is ammonium part of this equilibrium here? No, so what I'm doing is I'm getting rid of the ammonia and replacing it with ammonium. Ammonium is not going to have any impact on this. So this is like removing water in the well there. If I remove water on the left side, which way is it going to shift? It's going to shift to the left. Yeah. So remove ammonia, it shifts left, so we're going to go from dark blue back to light blue, basically. So this is just playing with Le Chatelier's, shifting it to the right and then shifting it back to the left. You see that? Now, how much acid should I add? Well, I got to add enough acid to neutralize as much of the ammonia as I can. So you just keep adding. So we aren't actually going to measure it. We're just going to just add, and then watch it. So they'll save a lot of time, you know. Okay, so the copper complex here is blue. The nickel complex here is green. So we're going to do this one. What's the name of this complex here? Hexa aqua nickel 2. Hexa aqua nickel 2 ion is going to be in equilibrium with this one, which is called hexamine nickel 2. And again, this one's going to be favored to the left. And so as we add the ammonia, we'll see it go from green to violet, the color change. The more ammonia we add, the more violet it should become. Okay, then we want to go backwards. In order to go backwards, what should we do? We're going to remove the ammonia by adding acid. Now, let's see what... We got to watch out because we're in this case, what's the acid? The acid is going to be HCl, which is a strong acid. And this is being added to the ammoniacal solution. Ammoniacal solution is like a highly concentrated ammonia solution. We got to add a lot of ammonia here. And this is going to be the 15 molar stuff. The 15 molar stuff is very powerful. You know, when you have ammonia cleaners at home, it's not 15 molar, it's way lower. If you get that 15 molar near your nose and inhale a whiff of that 15 molar ammonia, it's going to be overpowering, you know, and so watch out for this stuff. Don't get it under your nose. And that's what they call ammoniacal solution. It's like a maniacal concentrated solution, or it's just very concentrated. And so we'll add that. We're going to add it slowly because we don't want it to. It's going to generate heat, and we don't want it to get too violent as far as reaction goes. It's not, it's not terrible. It's not like a redox reaction. It's not going to be terribly violent. Okay, I think we're using 1 molar HCl, or 0.1 molar, so it's not terribly concentrated. Anyway, concentrated NH3 has a strong irritating odor. Do not inhale. If you come in contact with it, immediately wash the area with copious amounts of water. And so here we're adding the 15 molar ammonia dropwise until the color change occurs. All right, here, what's the name of this complex here? Hexa aqua cobalt 2. And this one would be called tetrachlorocobaltate 2. So we're going to look at this equilibrium and the difference here. So you're going to take a look. What does it look like before, and what does it look like after adding chloride? The chloride we're going to add is 12 molar. 12 molar is concentrated stuff. 6 molar is considered dilute. Avoid inhalation and contact with concentrated HCl. If you come in contact with it, immediately wash the area with copious amounts of water. And so we're going to add this dropwise to this and see, what the change is. If you don't notice a change, just keep adding more and more and more until you see a change. The shift to the right. Okay, one way we can shift this. I don't know if we're going to shift this one to the left. Okay. In this case, they're going to shift it by adding water. Adding water doesn't really change the concentration of the. What it does is dilutes these down. The other way we can do that is, you make these more concentrated. Let's say that you make the reactants more concentrated, it shifts to the right. You make the reactants more dilute, it shifts to the left. Now, we're making all of these more dilute by adding water. If we add water, this one becomes more dilute, this one becomes more dilute, and this one becomes more dilute. Well, what has a bigger impact? What has a bigger impact is on not the product side, but the reactant side. Because we have 1 to 4 versus 1 here. So it's going to make a larger impact diluting these than these. And so dilution will shift it. But another way we could do that is get rid of chloride. How can we get rid of chloride? What likes chloride? Silver, lead, and mercury. And so we could precipitate out. Like, for example, if we had silver nitrate, we could precipitate out the chloride, as silver chloride, and then shift this to the left. And so just react it with chloride. Yeah. Okay, let's look at this next equilibrium. This is a double replacement reaction. This is like your typical Chem 1A reaction. This is easy to shift. It's highly favored to the right, so it's easy to shift to the right. We're just going to add lots of sodium carbonate to make a precipitate of silver carbonate here. And in other words, we're increasing the carbonate. This is going to shift it to the right. Okay, so I can shift it to the right by adding more and more carbonate, but how can I shift it back to the left? I can shift it back to the left by getting rid of carbonate or getting rid of silver ion. I can't shift it to the left by adding more silver carbonate because that doesn't really change its concentration. It's still 100% silver carbonate. And so let's get rid of carbonate. What are some chemical properties of carbonate? Well, carbonate likes lots of cations, but how about its acid base? We could precipitate out carbonate with other things, but this is already precipitating out with silver. Carbonates, and so we don't want multiple precipitates here necessarily. So, for example, if we add lead, we'd get a white precipitate, but this is a white precipitate. 2 white precipitates. Another property of carbonate is it's a base, and so we can react it with acid. And so we'll take carbonate, react it with acid, we form carbonic acid. Carbonic acid spontaneously decomposes into CO2 and water. And so by reacting or destroying the carbonate and forming CO2 and water, this is going to shift to the left. And so that's one way. Another way we can shift it is get rid of the silver ion. How could we get rid of the silver ion? Well, we can precipitate it, but this is already precipitation here with carbonate. And so we need an ion that likes silver more than carbonate. You know, what ion is that? What ions like silver more than carbonate? So it gets more complex, the metathesis, because we're competing. You know, silver's competing. You know, there's a competition for silver between carbonate and whatever else you add in there. So this here we're adding nitric acid. Nitric acid to get rid of the carbonate. We don't want to use hydrochloric acid because if we use hydrochloric acid, you know, the chloride likes silver ions. So we're going to use nitric acid because nitrate and silver don't precipitate. Nitrates are all soluble. And so avoid contact with nitric acid. If you come into contact with it, immediately wash the area with copious amounts of water. And we're going to be using 6 molar nitric acid. Don't dump it in all at once, you know, little by little. Okay, here we have another one, you know, it's silver and chloride. Silver ions and chloride ions like to form a precipitate with silver chloride. And we're going to add, looks like we're going to add HCl. HCl is going to be the source of chloride. So HCl is a strong acid, but in this reaction, it's not being used as an acid. HCl is being used to supply chloride for the metathesis reaction. And so the more HCl we add, the more this shifts to the right and the more precipitate we get. There's going to be a cloudy white precipitate here. And so we can continue shifting this to the right by adding more HCl. How can we shift this back to the left? Well, we can shift this back to the left by getting rid of silver ion or getting rid of chloride. Well, how can we get rid of silver ions? Well, that's going to be complicated because silver likes lots of anions, but, well, it likes what? Chloride, bromide, iodide, carbonate, phosphate, sulfate, etc. And so there'd be competition there. But maybe it'd be easier to get rid of chloride. How can we get rid of chloride? One way we could get rid of chloride is by adding silver ions, but we're already adding silver ions here. What's another way of getting rid of chloride? We could add lead. If we add lead 2 ions, then we're going to get a mix, you know, silver and lead. We could add mercury and get another precipitate, but maybe we don't want to precipitate. And so let's not go metathesis. What's another chemical property of chloride? Chloride's a base. Can we add acid to neutralize the chloride? What if we added acid? Would that work? Add some acid like hydroiodic acid. Would it work? Actually, it wouldn't work because chloride is in the group of bases that are so weak, we consider them neutral. And so it's not really going to react with any acids, like your stomach acid or whatnot. So what other properties are there? There's metathesis, acid base, and redox. And so chloride is a reducing agent. It's not a very good reducing agent, but maybe if we used a powerful enough oxidizer, we could oxidize it. And if we could oxidize chloride, we can convert it into chlorine, which is a gas, and the chlorine gas can bubble out of solution. It's a yellow-green gas. So what's an oxidizer powerful enough to oxidize chloride? Give me one. Permanganate. Actually, permanganate is the oxidizer of choice for chloride. Permanganate, like potassium permanganate, is often used. And we mix potassium permanganate with chloride to generate chlorine. And it's very useful for generating small amounts of chlorine. You know, if we need large amounts, we'll just go buy a tank of chlorine gas. But if you just need a little bit, you don't want to buy a big tank. You just want to make some. And you can make some by just mixing potassium permanganate. So if we mix potassium permanganate with this, you know, the permanganate will oxidize the chloride. Silver is already oxidized. You're not going to oxidize it more. And we'll form chlorine. Chlorine can bubble out as a gas, and then that's going to shift this to the left. So that's good. There are other oxidizers we could use too on the list. But potassium permanganate is a powerful oxidizer. Sometimes we just don't want to mess with powerful oxidizers. And so there's another type of reaction that I miss. What type of reaction is that? So we looked at acid-base, we looked at redox, we looked at metathesis. Did I miss one? Yeah, I did miss one. We looked at Bronsted acid-base. Chloride is not a very good Lewis base, but it could be a Bronsted. It could be it's not. Oh, excuse me. It's not a very good Bronsted base, but it could be a potential Lewis base. But you know what? There's a Lewis acid here that's pretty good. The Lewis acid is silver ions. And so what are some good Lewis bases? The best Lewis bases are what donor? Carbon donor, followed by nitrogen donor, followed by oxygen, followed by halides. So even in Lewis, chloride's not that great in Lewis. But what if I take silver ions and then add a pretty good Lewis base? The Lewis base would be ammonia, and do this. So I take silver ions, react it with ammonia, and form this. What's this called? Diamine silver 1 ion. And in fact, this is an excellent Lewis acid-base reaction. This is heavily favored to the left here, products. If I look at the K value for this is very large. It's big. And so that means this is a very favorable reaction. And so all I have to do is add some ammonia. When I add some ammonia, you know, I got to watch out for redox. You know, I don't want redox reaction occurring between silver ions and ammonia. But in this case, this Lewis acid-base reaction is so favorable that it forms this stable complex. This is a fairly stable complex. The redox reaction, you know, you get some unwanted redox reactions if you heat this up. If I started heating this up, then I'd start worrying about potential redox reactions occurring. But since it's a room temperature, it's probably okay. Okay, so here we're going to remove the silver ions, and that's going to shift this to the left. So we just keep adding ammonia until this is all shifted. That is, we've dissolved all this precipitate just by doing that. And we're going to be using the 15 molar ammonia for this, which is, you know, the ammoniacal solution. Ammoniacal is this highly concentrated ammonia. Here's another one. We make a different color. This is more of yellow precipitate. This is going to be iodide like silver. This is a metathesis reaction from silver iodide. The more iodide we add, the more this shifts to the right. We can shift this backwards. How can I shift this backwards? One, I could get rid of the iodide. You know, iodide is a pretty good reducing agent, especially compared to chloride. So there are a lot more oxidizers that are capable of oxidizing iodide. You know, iodide's a big anion. Chloride's a small one, so it's much easier to oxidize the big one than the small one. And so iodide's known as a really good reducing agent. And if we oxidize iodide, we form iodine, I2, which is purple. And so that's one way. There we don't really need potassium permanganate. We could use a milder oxidizer, a much milder oxidizer for iodine. And so that's one way of doing this. Another way of doing this, to shift this to the left, is get rid of the silver ion. Well, we have a great way of getting rid of silver ion using Lewis acid-base reaction. And a nitrogen donor like ammonia or any amine would work very well to get rid of this. And so we can shift it back and we can dissolve all our silver iodide that we just formed. The final one is this. Heat about 75 milliliters of boiling water. Well, when we heat test tubes, you know, we have to be careful. One thing is we could try heating it over the flame, but that's too hot. The flame is extremely hot. You know, getting closer to 1,000 degrees C. Have you guys used the burner? No? No? Okay. This is a fancy Bunsen burner. This one on the bottom has a little valve, screw valve here. This is called needle valve. And the needle valve is not made for shutting it off. The needle valve is just made for controlling the size, to change it from a smaller to larger flame. It has a tapered needle at the end. You can see, if you could see this up close, you'd see it has a big dent around it. The big dent around it is because somebody tried to use this as shut off and then twisted it so tight it put a dent in it. You don't shut it off with a needle, you shut it off with the main valve here. And so let me close this. The barrel here is to allow air, so we can add more or less air by screwing around with this. So the matches, you know, just let these cool down and then throw them in the garbage. So I'll just turn on the gas a little bit. Get my flame to ignite. This is already pretty well adjusted here. I just blew it out, too much gas. If there's a long delay, we're going to fill up the room with natural gas. And so it's best to shut off the valve and then just start over again. All right, it's hard to fine-tune the flame using the main control valve. So we fine-tune the flame using the needle valve. So by screwing the needle valve in, that is clockwise, I can make the flame smaller. By screwing it out, I can make the flame bigger here. And so I just use this to fine-tune the adjustments. So you want a flame like this, that's structured. It has an inner cone. Do you see the inner cone? Okay, at the tip of the inner cone is going to be the hottest part of the flame. You know, so if we put a match right there, it ignites right away. But if we put a match here, it doesn't really ignite. Or up here, it just takes a little bit more time to ignite. Okay, if we were to heat a test tube, we don't want to hold the test tube with our fingers, so we use a test tube clamp. If we were to heat a test tube over the flame, we heat it over, not at the tip of the cone, we heat it in the soft part initially because we don't want it to get too hot. And then we can gently lower this to the tip here, and then that's going to be the hottest part of the flame. Now there's no liquid in here. If there's liquid in here, that's going to limit how hot it's going to get. This is going to get very hot. This is extremely hot glass here. It doesn't look hot, it looks normal, but you don't want to touch it. Like if I put my hand here, I can feel the heat radiating off this. And so this can cause some severe burns if I touch this. And so normally when you let this cool down, you point it away from you and then set it on like a ceramic plate there. One thing I do, or recommend people do, is something called annealing. You know, all semester long, people are stirring, you know, solutions with a stir rod, or trying to crush crystals. You know, they're trying to crush crystals here. or mix. And so all semester long, people are doing this. And eventually, at one point in the semester, somebody just barely taps the bottom of the test tube and pokes a hole right through the bottom. And I'm thinking, how did I just do that? I barely touched it. It felt like it didn't feel like there was any resistance. And what happens is, if you continue to do this, you're just stressing out the bonds a little bit, and you're tweaking the bond angle. As you tweak the bond angle, you know, the ideal bond angle for this is going to be 109. It's tetrahedral. But if you're tweaking it, eventually it gets tweaked to the point where it weakens so much it's easy to break. And that's what happens with this. And so what I recommend doing is, one, keep your countertops clean, because if this breaks and your solution spills on the counter or your precipitate, there's a chance you could recover it, you know, and not have to start over again. So if your countertops are clean, if there's a whole bunch of debris on there and other chemicals, then it's going to cross-contaminate it. Or two, this is what I do. What I do is, before I you know, at the beginning of the semester, I do a process called annealing. Annealing is you just heat this up and get it really hot. When you get it really hot, you know, the bond angles that are tweaked can relax back to the optimum bond angles. Well, so that the bond angle got pushed to 111 degrees. You know, by heating this up here, it softens it so that it can relax back to 109, you know, where it should be. And this process is called annealing, and it's just to regain the mechanical strength of this. Now, if I'm heating a solution in here, I don't want to point it towards my eyes, you know, because it could shoot up. I don't want to point it at my neighbors because it could shoot that way as well. And so you just point this away from everybody. But it's probably better not to heat, because usually when people heat it with a Bunsen burner, it splatters out. It gets way too hot, splatters out onto their neighbor, onto themselves, onto the counter. And so what we're going to do is we're going to use a hot water bath instead. For a hot water bath, we need a ring stand like this, and we need some rings. We have the rings in a wood bucket or wood boxes back there. They're underneath the counter. Actually, they aren't. They're on top of the counter, way in the corner of the lab over there. So, first thing is we need to adjust the height of the ring. We want to adjust it so that the tip of the cone is right at the base of the ring. And then what we want to do is, we don't want to focus the heat on one spot. We want to distribute the heat over a wide area. So this is a wire gauze. This is an insert there. We can put that there. That's going to distribute the heat more evenly. This one has some junk on it. Let me use this one. This one's cleaner. This is hot, so we can set that aside. Okay, then we're going to set up a water bath. Normally with water baths, I like to use DI water, but the cost of DI water has gone way up, and so we're spending a lot of money. It's like almost $1 a gallon now for the DI water. So we're going to just use tap water, which is still cheap. And we'll fill the tap water like a third to a half full. You don't need to go more than half full on this. And then we'll put it here. But since we live, you know, in California, earthquakes might happen. And if this spills, boiling water can cause second and third degree burns. We're going to use this as a support here, so that it can't get accidentally knocked over, you know, which has happened in the past. Okay, now, oops, shoot. You see how hot that was? I should have pointed it away from me and laid it on a ceramic plate, which I didn't have, but I just melted my goggles. Gee, I thought I was cool enough, but it certainly wasn't cool enough. And it's still very hot. And I'm not going to put this in the flame, otherwise it's going to stink up the whole lab. So let me put this aside here. Get this one here. Okay, now I have this. Usually you just leave the clamp on here and then you can heat it here. This is going to limit how hot. You know, the max temp it can get is 100, you know, as long as there's water in here. If all the water evaporates, then the temperature will skyrocket. So keep an eye on it. If you need to fill it more water, just add some more water to it. Okay, so what we're going to do is we're going to do this. We're going to put the cobalt 2 chloride solution in the boiling water. Look at its color. Okay, and then what we're going to do is we're going to get another beaker. And over here, there's an ice bucket. There's a red bucket here. Get some ice. And what we want is we want ice water. You know, ice water is going to cool things down more rapidly. And then we're going to take this, look at the color, and then cool it down in ice water, and then look at the color, see if there's a color change. And temperature is going to shift it one way or the other, you know. And so we can go back and forth by heating and cooling. Shift it left, shift it right, whichever. We'll analyze it later. Just take your observations. You can take your observations just on regular notebook paper today, or if you have your lab notebook, you could use that. If you have your lab notebook, don't use the first page. Leave the first page blank. But you can write after the page 2 on. Just your observations. That's all we're going to do today is take our observations. Next week, the report will be due. Okay, are there any questions?
If we turn off the lab, can we just write on the lab?
You can write on the lab. That's fine. Okay, you can work individually or you can work in groups if you'd like. You know, if you work in a group, then, you know, you want, because with COVID, you've missed out on, you know, prior lab experience. So even if you work in a group, you might just want to each do it, you know, so you get more practice. The more practice you get, the better skills you'll develop in wet chemistry. And so I just recommend, you know, trying to get as much practice as possible. Okay, well, that's it. So go ahead and get started.